Today we are going to talk about something completely different from anything that we've covered so far. So all of the data analysis that we've done in class so far, whether we're talking about linear models, parametric models, to semi-parametric, non-parametric, if we're talking about causal stuff versus we're talking about predictive stuff, all of that. What does all of that have in common? It's got y and x's, and we kind of want to understand the relationship between x's and y's in different ways, right? We may want to understand about how x might predict y, we might want to understand how y changes as x changes, right? So that covers very generally most of what we've talked about in class so far. But today, what if we focus instead on just the x's? Okay? So what we're going to talk about today is known as unsupervised learning. So this is examining undetected patterns in data. So it focuses on settings with only explanatory variables. No response variables. Therefore, we are not interested in prediction. We rather want to identify subgroups among variables. And importantly, unable to conduct validation. Right? Validation is all about, in my response variable, like some measure of how well I'm predicting or estimating that response. But here, there isn't any of that. So kind of at the end of the day, when we talk about unsupervised learning, there isn't like a right answer or anything like that. Otherwise, this would be supervised learning. You would have some guidance in terms of, what would the right answer be? So again, this is going to be pretty different from most of what we've done so far. There are several different classes of unsupervised learning. And the one that we're really going to focus on today is clustering. But that's not the only way you can do unsupervised learning. There's things such as dimension reduction, which is a way of like manipulating data in certain ways. But clustering is kind of the focal point for today. It's about grouping things together and understanding different tools that we can do, that we can employ to group things together. And kind of big picture wise for clustering, it's all about, if you think about what makes data grouped together, at the end of the day, it's just different measures of distances of data, okay? And so we're gonna dive into how we can take advantage of these like distances and and see how there are a variety of clustering approaches. Yeah, and the examples today I think are kind of fun. We can see how interesting you can get some kind of outcomes with this clustering. Okay, so clustering approaches. First one we're going to talk about is k-means clustering. Also known, also a type of centroid clustering. So this is a simple approach to partition data set into k distinct non-overlapping clusters. Okay? And k must be pre-specified. Can anyone guess how we choose k? No, trick question this time. Right? Remember, we are unable to conduct validation. Yes, so I know I said the answer would always be cross-validation, but special case today, not the case. We'll talk about how to do that in just a moment. So, as usual, we're going to start out with the math, which is like kind of, well, I'm not going to say uninterpretable, but maybe a little bit less straightforward. And again, definitely not something you guys have to memorize. K equals 1, K, just for your reference. It's going to look something like this, times the sum I prime, sub-element of ck, sum j equals 1 to p of xij minus xi prime j squared, where ck is number of observations in the kth cluster. Okay, don't worry about the math here. Let's instead talk about the procedure, so algorithm. 1, randomly assign 1 minus k to each observation. Okay? 2, iterate until no more changes. And the thing that we are iterating is for each k cluster, compute centroid. B, assign each observation to cluster with closest centroid by Euclidean distance. So note scaling. So normalization is critical. Okay? So this is like a pretty basic algorithm, but it's actually pretty powerful in terms of what we're able to do. And so I'm sure some of you guys have probably heard of k-means or have used k-means before, but let's kind of demonstrate a quick example, okay, of this algorithm. All right, so I'm gonna make a plot here. And let me actually change this. All right, so we're just gonna look at we're gonna set k equals 2 for now. So now I need to randomly assign a group to each observation. And I'm just gonna classify these guys into groups. And I'm gonna represent that as red and blue. Okay. First point. Someone say red or blue? Red? Okay. This guy is gonna be red. Actually, let me do it like this. Yeah, okay, next. Red or blue?
Blue.
Blue, okay. Next guy, red or blue?
Blue.
Blue. Okay. Next one, red or blue? Red. Red or blue? Red. Okay. Red or blue? One more.
Red.
Red. Okay. Other side. Red or blue? Red. Alright. Maybe there's a better way to do this. Alright, I'm just gonna make up the rest. Alright, we'll do something like this. This. We'll do red for this guy. Great. So, for each, so I've randomly assigned 1 minus k to each observation. Thank you guys for helping me with that random assignment. And what I need to do now is step 2, iterate until no more changes. Okay, 2a, for each k cluster, compute the centroid. So there's a red group and a blue group, and we need to compute the centroid of those things. Okay. Where is the centroid for the blue one? Someone can say stop, whatever. Maybe more on this side, right? Because there's more blue points. So maybe if I'm like in the middle, I might move over here a little bit. And then for the red one, there are twice as many points on the right as on the left, and so if I computed the centroid, it might be something like over here. Okay. So in that case, maybe my red centroid looks something like this, and maybe my blue centroid looks something like this. Okay. Everyone following along so far? We're good? So now 2b, assign each observation to the cluster with the closest centroid. Okay, so we can kind of visually see this, right? All the points on the left are closest to the blue centroid, and all the points on the right-hand side are closest to the red centroid. So I'm just gonna reassign everything. Let me first get rid of these guys. So this point becomes, these points become blue, and these points become red. Good? Now we're gonna iterate. So back to 2a, for each k cluster, compute the centroid. My my centroid is now probably somewhere like here for the blue, and for the red, it's probably somewhere like this. Okay. To B, assign each observation to the cluster with the closest centroid. So hopefully you guys can see we have arrived at kind of a final solution, because now when we reassign the points, none of the points change color. So the groups are now stable, and in fact if I iterate this again, nothing will happen, right? Everyone seeing what's going on? That's it. That's k-means k-means clustering. Pretty straightforward, kind of similar in some ways to the KNN, if you guys remember. But with the KNN, there is kind of like a right answer thing, whereas this one, yes, I'm kind of looking at neighbors in some way, but importantly, we don't have any response variable or anything like that. So, you know, purely from the distances that these points are from each other, we're able to cluster things into, wrong color, into these groups. Okay? Any questions about this? Okay. Oh, yes.
Uses for this?
Uses for clustering. If you want to group data into groups, this can be a pretty nice way of doing it without
Bias?
no, nothing's biased, right? Because we're not like comparing this to anything. But if I'm not trying to analyze data relative to some kind of response variable, like clustering is a very powerful means of being able to do that. Let me actually show some examples, and maybe that will help.
Yeah, well, the Euclidean distance is just the shortest distance, right?
Yes, shortest Euclidean distance to the centroid. Any other? Yes.
Why does it need to be a random assignment for the observations? It seems like we would get to the same result regardless of how like the blue and the red were spread out again.
Yeah, oh, actually, that's a good, do you always get to the same result? I think so. No, actually, there must be examples where you could get trapped into some, it'd have to be a pretty specific thing.
Like a
But-
whole minimum or something.
Yeah. But as far as why do you do it randomly, like how else would you do it? Because there aren't, remember, like we're not assigning groups based off of any like observation of any kind, so you don't really have anything to go off. And it's really just a starting point, because you're always gonna like iterate towards this type of thing, towards these groups. So it shouldn't, I think for most examples, won't make a difference. Yeah. Okay, so I have in the class notes, or the class files, loaded a couple of example data sets, which you are welcome to grab from Canvas. And these are the data sets that we are going to play around with today. Oh, great. And let's take a quick look at what these data sets look like. Okay. So These guys are a little crazy. These are synthetic data sets that are essentially putting points into like various points in space, and you can see how the points are kind of laid out here. There's kind of groupings of these guys, right? Even more, but with a little bit, with groups of points that might overlap a little bit. Here we have something that looks like this, and then some crazy looking guys over there with points that are kind of spread all throughout, but you have higher density of points in certain areas. Okay. So I think these are kind of nice examples to demonstrate the ability of different clustering algorithms to group certain things together. So visually, right, we may point to groups of points kind of more obviously, right? And so then it's about how some of these tools work to replicate kind of what we mentally are pointing out as what might be clusters. And so these examples, I think will do a good job at showing the capabilities of various tools and maybe some of the pitfalls of some of these tools. Okay. So let's look at k-means.ex, k-means ex1, comma, dot x, comma, y. Comma 2. Okay. So I'm using the k-means function, and all I'm doing is I'm putting in my data set for the things that I want to cluster, which is my x column and my y column, and I'm choosing 2 clusters. Okay? So we're doing example 1, so we're doing this first one here, and we're just gonna do 2 clusters. And let's look at what that looks like. Okay, hang on. So my x's are going to be x, my y's are going to be y, and the color, right, which is what I want to show the groups, is going to be this thing, k-means.x dollar cluster. So let me actually quickly show you what the output of the k-means function is. Looks something like this. So we have cluster means for 1, x at 85, y at 52, for group 2, 37 and 12. What do you guys think this is? Yes, the centroid. This is where the final centroid is that we've arrived at doing that algorithm, right? And then clustering vector, what do you guys think this is?
Assigning the dots to the group.
Yeah, exactly. So every point in my data set is now assigned a 2 or a 1, depending on what group it is. And then you have within cluster sum of squares. So this is all of the distances to every point within a cluster squared. And we can look at, I mean, those are basically the only statistics there are to look at. Yeah, size, number of iterations, if there were any errors. Yeah. So in this ggplot, the colors are my group assignment here. Okay, so if I run this, let's see what happens. Cool. Okay, so I probably have a centroid around here, and there's probably like a centroid somewhere here. So all of these points get assigned to this centroid, this one here, and then these ones would be closest to the one here. Okay. What about this? That's for 3 clusters. You end up with something like this. And with 4 clusters, we end up with something like this. What about 5? So with 5 clusters, we have arrived through that algorithm where we iterate to actually splitting that group in half. And that's, I mean, visually, right, we may have some preconceived idea of like, oh, these should belong to certain groups, but there, again, there is no right answer here. Right, I could do 6 if I wanted and see what happens. Okay. So, okay, I said there's no right answer for these things. Oh yeah, go ahead.
The points are, there's like a physicality to this representation, or how are they
They're just like,
different from each other? Like the alterations or the difference in space represent the the 4 variables?
so,
Up there it says 1,000 observations and 3 variables, but they're like 4 clusters.
so variables are just x and y, and then the cluster that I assigned to them. So don't think of this as like there's no relationships between anything. Okay, these are just points in space.
Points in space.
Yeah. So then, the idea, right, is, so imagine these points are all black. Okay. And I'm like looking at these points and I can say, oh, well, these points look like they're close together, so that's one group. This point looks like they're grouped together, so that's one point, and so on. Right? That's something we might intuitively do. And the idea is there like a quantitative way of doing that? Is there a more kind of rigorous way of doing that? Because actually, you know, easy enough to do when we look at it like this, but you can imagine if there was another dimension, it might be a little bit harder. You're looking at like clouds of points in 3D, but then if you do 4 dimensions or 5 dimensions, now it's like you can't visualize it, right? And so getting an understanding of how this works in 2D will help you understand how this works in many dimensions. Yeah? Okay. So while I said there isn't like a right answer for the number of Ks, there are some principles and guidelines that people have tried to use to determine like a rule of thumb for choosing K. Again, in this case, we can be like, oh, it's obvious, there's 4 clusters, right? But if you're looking at data in many dimensions, you wouldn't visually be able to say that. So how do we go about doing this? So I'm actually going to, so this part you don't need to follow along. I am going to put in a custom function where I'm going to run through a whole bunch of different Ks and test them. Or not test them, there's nothing to test. But I'm going to record specifically the within sum of squares. And people use that within sum of squares value in order to help determine the right number of clusters. So don't worry about the function. All this thing is doing, where I vary .k, is I'm going to do the same thing that I just did, except I'm going to check 2 clusters, 3 clusters, 4 clusters, 5 clusters, all the way up to 10 clusters, grabbing that within sum of squares value that I was just mentioning. And then I can plot this. Ooh. Here we go. Wait. Okay, wait, that's not supposed to happen. Let me do this. Okay, there we go, that's a little better. It shouldn't go back up, I don't know why that happened. And I don't think that happened before when I tried this example, but regardless, usually it looks something like this. Actually, even this is a little bit unusual. But this is called the elbow method, or the kink method. If you imagine that this is somebody's arm, the location of their elbow is where you would choose the right number of clusters. Yeah, that's kind of what we're going off here. But that's a very common procedure in k-means clustering, to do something like that.
And why? Because those would be too far apart and these are too similar?
No, it means that you've, right, the size of the within sum of squares is telling you something about how far your points are from the centroid, and you get a big gain at some point where points have coalesced around your centroid, and as you add more and more centroids, usually everything will always get closer, right? If logically, if you think about this, right, adding additional centroids should move points closer to that centroid, because you're reducing distances compared to your previous number of k. But those gains will be smaller and smaller, and so you want to get the k that has the biggest step reduction, and then say, okay, we're done. So that is emulating essentially what's happening with an elbow plot. Yeah.
Could you go for 4?
Yeah. This is a little messed up looking arm though, so.
It's a broken arm.
I would say 4 because I know I kind of know visually that it's 4, but you can see kind of how you could get 4 from something like that, right? Okay, any other questions? So if I let's just kind of look at let's look at k-means applied to some of those other plots, some of those other examples, just to kind of see what it does. And we're gonna vary what it looks like. Okay, so in example 2, I'm plotting the elbow method. So if this is the arm, what do you guys think? What is like, where would we choose our K? There isn't like a right answer here. You would choose 5? Okay, 5 or 6, yeah, sure. So let's see what that looks like. So this one, alright. So we're gonna look at a whole bunch of different clusters. So 2 clusters, 3 clusters, 4 clusters, and so on. Yeah, some of you guys were saying 5 or 6. That's what you would get. If you think of these as kind of distinct groups, visually, I don't know, does anyone see a good one?
22.
22. Okay. This one's kind of split in half.
18.
And maybe this part, yeah. But it's kind of hard to get a good sense, right? Like 18 looks maybe decent, except that you have some stuff going on over here. Okay, so right, you guys can see when you're doing centroid-based ones, you're not always going to get like perfect results. And I'm saying that again, kind of facetiously, because there aren't right answers here, right? This is just, we're just like trying to group things. If these were actually grouped with clusters, we would have like a response variable, and then we could do a different procedure to like figure out which ones belong to which, right? But this is all kind of done as unsupervised. Okay, so that's example 2. Let's do the same thing for example 3. Probably 2 clusters, right, visually, but for something like this, you can see that doing centroid stuff would be really hard for things of this shape, right? Because for 2, if I have one centered in there, well, there's all these points that are gonna be changed, and same here, right? My centroid is like here and here. Okay, and so this might be a particularly difficult example for k-means clustering to deal with. And let's look at the last one. Oops, what did I do? There we go. Okay, this might take a second to render. Do you guys remember what this one looked like? It didn't look like this. Yeah, so you can see here, this doesn't look really like anything like our original one, which had points kind of spread all throughout the plot, but there were higher density of points in certain areas. Okay, and so just as a reminder, this plot is this guy here. So k-means clustering, particularly bad at differentiating groups based on the density of points. Okay? All right. Questions? Okay, so then we are going to look at a different approach. So what is another type of clustering we can do? So there is something known as hierarchical clustering. Also known as a collaborative or bottom up clustering. This is an alternative method that does not require pre-selecting your K. Results in tree-based representation known as a dendrogram. Okay. Okay, so I may have points A, B, C, D. These are called leaves. And then I have branches, like so. Okay, and so let's see. The farther up the tree branches fuse, and the more different the leaf observations are. No conclusions can be made on distance horizontally. Okay? And so that means I can't look at how far things are in this direction. It's all about the branching. So A is closer to B than it is to C and D. But I don't know if A is closer, sorry, no. I don't know how far B is relative to C and D because of the distances horizontally, okay? You could like flip the tree and it wouldn't make a difference. Okay, what does this have to do with clustering and how do we generate this tree? So one of the reasons that you don't have to pre-select a K is that I can choose it once I've selected the tree. So if I were to snip this tree right here, that would mean I've created two clusters, one right here and one right here. Hopefully everyone can see that, right? If you snip the branches, you now have one group over here and one group over there. So snipping right there, so cut here, and I get two clusters. And if I cut here, how many clusters do I have? 3, yes, exactly. So this would be 3 clusters. If I cut here, I would have 4 clusters, and so on. And so this tree is designed in such a way that I can cut wherever I want and group them based off of those cuts. Okay? So now the question is, how do I build the tree? Because once you built the tree, we can create the clusters, right? Hopefully everyone can see that. So similar to k-means clustering, there is an algorithm to do this. And you start with each observation is its own cluster. So you have n total. Then the two most similar are fused. So you can have n minus 1 clusters. And then you continue until a single cluster is left. Okay? So I have a bunch of points, spread them all out. I take 2 of the points that are the most similar amongst all those points, and I fuse them. And then I move on, I look again, which 2 points are the most similar, fuse them, and continue doing that until you've built up your whole tree. Questions? Yes?
Does this mean you have equally sized clusters?
Well, I'm so glad you asked. No, in fact, it depends on something that I haven't explained yet, which is, does anyone have a burning question yet looking at this algorithm? So what do I mean when I say most similar? So similarity, basis of Euclidean distance. And that's fine for individual points. Okay, great. So I've got, let's say I've got 3 points like so, x, y, and this is A, B, C. Okay, and maybe we have some other points like this. Let's say D, E, F. So I go A, B, C, D, E, F, and we say, okay, great, those guys look similar. I'm gonna group them together. There's like my first fused branch. Okay, now what? I can continue to do the similarity for individual points, but how do I do similarity with fused points already? Okay. And it turns out there's 3 different ways that this is done. So, similarity on basis of linkage. And the 3 ways is on linkage of this of your centroid. So 1 is complete, 2 is single, and 3 is average. So this is largest dissimilarity, smallest dissimilarity, and then average dissimilarity. And going back to your question about the sort of balancing, in other words, like, are you gonna have something that looks like this? What is a good way to show this? Okay. I'm not allowed to do that. Versus something that might look like this. Because this is known as the balancing of your clusters. So think about if I cut here versus if I cut here to make 2 clusters. The top one is a lot more balanced, right? Because you have 3 and 3, whereas this one you'll have 5 and 1. And average and complete linkages tend to have more balanced clusters, whereas single tends to have less balanced clusters. Okay, any questions? Yes.
Is it incorrect to think of it kind of like in genetics, how you build like an evolutionary tree?
I don't know how you build an evolutionary tree, but possibly. to say,
If you're like comparing like a DNA strand, for example, as you're
yeah,
trying to get clusters of that.
yes. Are you looking at the parts that are least similar, or are you looking at the parts that are most similar? Yes, it would be something like that.
Okay.
And that would let you build your tree in very different ways.
Okay.
Maybe so let's jump to the example, because I think this is actually going to be the best way to show the differences between choices of linkage in a hierarchical cluster. Okay, so let's jump on over here. We're going to do our hierarchical clustering. Okay, hierarchical clustering, I'm going to load in my examples again. Okay, and nice thing here, I don't have to specify any parameters or anything like this. Quick word of warning to reiterate something I said earlier. Clustering is based off of distances. If you look at the data here, all the scales of these points is the same. But if it's not, you probably will want to normalize your data, otherwise you're going to get pretty funky looking clusters. Okay, so to do the cluster, we use the function hclust. Now we don't need to make any specifications for how many clusters, right? Because it builds the whole tree. And then method specifies which of the linkages that we want to do. So complete, average, or single. So we're going to look at example 1. And boom. Yes.
If EX1 has more than 2 variables, how does it know what's your X and what's your Y?
There are no x's and y's, remember?
Okay, so but which 2 is it calculating the distance between all of them?
Yeah, so yeah, I should relabel these because think of it more as x1 and x2 as opposed to an x and a y. And then now, so let's suppose I have x1, x2, and x3. You can still plot those out in space, right? So in 3D, I'll have a point here. I might have a point here, and then maybe I have a point over here.
Okay.
So then, when I'm doing the algorithm, right, it says each observation is its own cluster, then the 2 most similar are fused. So I have 2 points here and 1 point here, which two points we get fused.
Okay. So it
These-
takes
these
all
two.
of the columns as its own dimension.
Yeah,
Okay.
exactly. And then it'll calculate the distances. Yep. So the code is pretty straightforward, hclust. Let's look at what hc complete looks like. Not much. Cluster method, complete, distance Euclidean, number of objects. Let's plot these guys. Okay, and you can literally plot the output of your hclust function, and this looks like this. This is the tree for example 1, which has 1,200 points, okay? So it's a pretty dense looking tree down here. It's not altogether that useful to plot these trees all the time like this. But what I want to show is the way that the tree is built, right, is the branches fuse at higher and higher points. So I can make a cut up there. For 2 clusters, I can make a cut here for 3 clusters. I can make a cut here for 4 clusters, cut here for 5 clusters, and you can actually do that all the way down. So when you end up deciding to group them, you get to choose how you're gonna group them, and then, yeah, you can cut all the way down to the bottom, and you'll get, 1,200 or whatever that number was, number of clusters. Also note that, would you guys say that this tree is balanced or unbalanced? Balanced. And what do I mean by that is if I cut somewhere, the number of points within a cluster tend to be roughly similar, okay? And you tend to get that with complete linkages. Similarly, here's what the average one looks like for the tree. It'll look something like this, okay? So complete and average tend to be somewhat similar. But let's take a look at single. You'll see here that this is a very unbalanced clustering. If I cut there, the number of points in here versus all of these guys is very different. And that continues on even as you cut down the tree. Okay, so I've written some functions that let us look at this in a little bit more detail. So let me paste those over here. Rid of some stuff really quickly. We're going to look at all 4 of those examples in just a second. Okay, I've written this function that's running all the different linkages types. Okay, I should mention the way that you extract the number of clusters is using a function called cut tree, or CUTREE. And there is an option that lets you essentially specify like where you're making the cut for the number of clusters. And when I do that here, I am showing, for example 1, the number of, so this is 2 clusters, 3 clusters, 4 clusters, so I'm making cuts in the tree to separate the points into these groups. And as we go from left to right, you have more and more clusters. And then from top to bottom, we're looking at the average linkage, complete linkage, and single linkage. So yes, if we look at the cluster 4, which is maybe how we're kind of looking at these things visually, we can actually see that single, complete, and average have all grouped the points kind of in the way that we have expected, right? But when we look at average, complete, and single, we can see the way that it clusters things is actually really different. Okay, so in the average, the fifth cluster, it's just grabbing a couple of points out there. In the complete, it's divided this cluster in two. And in the single, it's looking at the one different guy, has its own cluster. Okay? Okay, any questions about this? Yeah.
So you would have to look at this in all of the dimensions to figure out the best one?
No. There is no best one. And you would not be able to really visualize this in this way if you were talking about trying to do this in multiple dimensions. Once you're past like 3 dimensions, you can't do this. But what I would say is the point of this example is to kind of understand a little bit about the behavior of the different average, complete versus single. They're gonna try and do different things to like cluster the points. Okay. Other questions? So let's keep going here. Here's example 2. This is example 2 looking at the complete. I can't really do 3 rows for everything. It's a little too crazy. But when you have relatively balanced groups like this, I think generally this choice of linkage might do maybe a slightly better job. You can see how this compares to the average. I think this one is pretty similar. Yeah, looks something like this. Versus, I think you'll see it's pretty different if we do, oh, did I not even do the single one? Oh, here it is, single. So instead of like, especially early on, instead of dividing points out, it's gonna like leave the least similar group out of the cluster essentially. And so you can start to see in this one, single clusters kind of entering into groups one by one as we move through these. Okay? And here are our 3 different methods. Okay, so now we can kind of see one of the unique things about a single when you kind of leave out groups that are as dissimilar as possible, as opposed to looking at average or complete groups, right? This is actually successfully able to differentiate these like weird shapes. And you can see these are going to be a little bit more similar to the way that our k-means operates. Still a little bit different, but distances in absolute terms. Whereas here, it's just going to try and find the most different point from the cluster. So single is throwing out points kind of one by one. Okay? So in the hierarchical clustering approach, we can have very different ways still of doing these clusters. All right, and the last one, let's look at example 4. What do you guys think? Still not great. So when it comes still to points that have really high densities, right, these distance things are still not doing a great job. And so clustering here, we're not observing maybe necessarily what we're expecting. Okay? Any questions? All right. Then let's move on to the last example for the day, or the last tool for the day. We're going to talk about DB scan. Also known as density based spatial clustering of applications with noise. All right, so given a set of points in some space, it groups together points that are closely packed together. So this is points with many neighbors. Marking as outliers points that lie alone in low density regions. Okay. So our algorithm is something like this. For each point in the data set, if number of points within epsilon neighborhood is greater than or equal to minimum points, classify as core points. Otherwise, label as noise. 2. Expand cluster. For each point that is a core point, form a cluster. Any core points that can be reached is a cluster. Any noise points that can be reached but less than or equal to min points, add as border of cluster. All right, yes.
Larger or equal to minimum PS?
Larger than equal to, so there's 2 parameters that you have to specify with dbScan, which are epsilon, oh my god, I can't draw epsilon. Epsilon and min points, PTS, or minimum points. Okay, everyone understand? This make perfect sense? Okay, let's actually walk through it. Not as it's not as confusing as it seems, I promise. Let me jump on over here. Okay, let's see if I can do this correctly. So I've got some points in space. Do something like this. Yes. Okay, we're gonna say min points equals to 4, and we're gonna say epsilon is equal to this distance. Maybe a little bit further. Okay. All right. Then actually, let me put a point out here. So what I'm gonna do is I'm going to go through my algorithm. Let's see. So for every single point, I'm going to, okay, in 2D I would be drawing a circle, in 3D it'd be like a sphere, but I'm gonna look at the distance equal to epsilon. Okay, so this will be like this. So this is the distance epsilon, and if I do that in all directions, I draw a circle, like so. Are there 4 points within the circle? Yes? 1, 2, 3, 4, 5. Okay? So this is going to be a core point. Okay, so we're going to say this is equal to core point. Everyone following so far? We're good? And I'm going to repeat this exercise for every point. Oh, don't make me draw circles. Okay, there we go. Great. Are there 4 points within the circle? Great. So that is a core point, and if you do this several times, then you will find that all of these guys are core points. Okay? We following along? Which means that anything that's not a core point we call noise. Okay? So this is equal to noise. So the blue points together make a cluster. Okay, so any core point, so in step 2 of our algorithm, we assign and form a cluster. And that cluster is for everyone that shares these min points. Let me draw one more circle here. Like so. No. Okay. So that was part 1 of step 2, part 1 and part 2, all the blue points become one cluster. Part 3, any noise point that can be reached but has less than or equal to the number of min points, right? Oh, actually, if I draw this needs to be including some of these guys. There we go. So if I draw a circle around this noise point, like so, and like so, and maybe one over here, like so. Okay, so I'm going to call these points 1, 2, and 3. So does 1 qualify for min points, 1, 2, and 3? No, right? There are not 4 points within that circle. But there is at least 1 core point within epsilon distance of that point. And so if you look into the algorithm again, any noise point that can be reached but has less than or equal to the min points, we add into the cluster as the border of the cluster. So these guys, yes, you guys get to be blue. And actually maybe I'll color it yellow. Okay? So 4-point border point. Okay. So our cluster is these points, and this guy is noise. Everyone following along? Any questions? Okay, so this is another type of clustering method, and hopefully you guys can see at this point we're doing grouping, we're doing clustering of all these points, but they're doing it in a pretty different way for all of them. And we can then apply this and see what happens in our examples. Jump on over here. DB scan. So we will need a couple libraries here. We're going to need DB scan. We'll need FNN, and we'll need FPC. I will the code today is a little bit longer, and so I'm kind of I know I'm doing a lot of copy and pasting here, but yeah, you guys can look over the code. It's already actually loaded on Canvas already if you want to kind of follow along. I'm reloading my 4 examples. Okay. So let me run this. Okay. In the k-means clustering, we have one parameter as an input into running the model, which is what is the number of clusters that we want to look for. And we use the elbow method for that. In dbscan, what are our 2 parameters? Yes? And minimum number of points. Okay. So, not going to go into the theory behind this, but it is again just like a heuristic that people use, similar to the elbow method. You can plot the points sorted by the distance, and the epsilon that you choose is again based on the elbow method, like the kink in the plot. So kind of a similar type of idea as in the k-means clustering algorithm. You want to get to a point where you're starting to get large distances between points, and you want to make some kind of cutoff there. So k equals 3. You can plot this with k and n disk plot, and then I can run the actual DB scan here, and I've chosen to do, so these plots may actually look a little bit different, depending on our minimum number of points. Okay. I'm doing 3. I saw there was about 0.8, so we can look at what this looks like here. Okay. So if I choose 3, or sorry, yeah. If I choose min points equals to 3, and then I run this, then these are the groupings. Look something like this. These are actually different groups. And then you have noise, and then you have a couple of other groupings, or actually these may actually be the border points for those clusters. So K here, importantly, does not refer to the number of clusters. It's referring to the number of points that I want to consider in that like circle that I'm drawing to form the core point. What's the minimum number of points that you need for a core point? So let me rerun the very original plot here. This guy. Okay. So one of the unique features of this plot is that there's varying densities between the groups, right? So these guys are like packed in really close together where there's like a bigger spread here. And when you have situations like this, right, density-based clustering algorithms might have more difficulty differentiating these guys as part of a cluster, right? Just because they're like farther away. So large variance in density, densities and distances between groups of points are going to be difficult for dbScan. Make sense to everyone? So let me do this. Okay. So harder to display some of these across because unlike the previous ones, we're kind of varying multiple parameters. Here I've stuck to leaving it at minimum number of points equals to 3, but I'm changing our epsilon distance, so how far I get to look in that circle, okay? And we can see that when I look really close, when my circle is really tight, you tend to have more and more clusters, right? Especially in places that are less dense. And as I increase the circle and what I'm allowed to include in the minimum number of points, we see this kind of thing happening, right? And eventually we can see that now it's kind of differentiating. It's differentiating or including groups of points much farther out, although we do still get like noise in many of these cases. Okay? Questions? Clustering is not very exciting for you guys today. Okay. Okay, so I'm just gonna finish off and let's finish off just looking at the application of dbScan to the rest of our examples, just to get a sense of how it's gonna work. Okay, so example 2 over here. And again, feel free to look at this on your own later. So here, this was our example 2, and we can see, again, so this is, let me see, what was my min points for this? Still using minimum points equals to 3. And what you can see is that it's already spitting out all of these clusters at the beginning, and then as I increase the distance, right, for the circles, we start to get some more refinements. Now, if I continue to increase the distance, okay, let's say from here to here, we still see some of the noise in black circles getting classified there, but then what happens if I make the distance encompassing all of the points?
You start to get fewer borders.
Not only that, you start to get fewer clusters, right? Because imagine that my min points is 3, and the size of my circle is like this, then all of these points would be core points, right? And you would have one cluster. So here, you know, the circle's starting to get bigger and bigger, and as that happens, it's going to swallow up more and more of these groups. Okay. Does that make sense to everyone? Okay. Let's do the next one. So example 3 is the one with the 2 U shapes. What do you guys think is going to happen? What do you guys hypothesize? Is it going to do a good job or a bad job? Good job? Bad job. Yeah, so if you think about what's happening, I have, you know, these 2 things like here, all I need is a certain number of neighbors close enough to classify into core points, right? So I think it's gonna do all right. When your distance is too small, it's generating too many clusters. We can see all of that happening here, here, here. But suddenly, once your circle is large enough, you will be able to hit all the points that are nearby each other, right? We're doing a density thing. There's a continuous density of points like this, and there's a continuous density of points like this. So, DB scan actually works pretty well for this example. Okay. All right. Last example, number 4. What do you guys think? So just as a reminder, here is example 4. Oh, no, it's not showing. All right. Okay, that's example 4. What do you guys think? Is it going to do well, or is it going to do poorly?
All of the methods you've shown so far haven't done great.
Yes.
This one, so hopefully, when we're about to test.
Yeah, and right, what I was describing is like distances between points weren't getting shown very well, but there's a big differentiation in the density of points, which hopefully something called density-based spatial clustering is going to do good, right? So let's take a look. Oh no, what happened? I subscript out of notes. All right, one sec. maybe this did not finish. So, DB scan can be maybe a little bit more computational intensive in some regards, because it's having to draw many of these circles and then doing this like classification thing. Well, not like classification in a regression sense, but okay. So let's give it a quick moment to finish. Hopefully it will. Okay, there we go. And let's try this again. So let me dev off. And voila. Okay. Small circles, big circles, and then kind of in between. Yeah, we can see does pretty well, I think, in 7 and 8. Okay in 6. This little circle in the middle is getting grouped into these guys, but generally speaking, right, this is way better than any of the other clustering methods that we've done. Yeah, so when things need to be differentiated based on the density of points, DB-scan is your answer. Okay. Yeah, and that's it for today. Our kind of departure from supervised learning for one day. We are doing, unsupervised learning, quick overview of a couple of different grouping clustering methods, and hopefully this overview has shown you guys a sampling of the tools that are used in unsupervised learning, and importantly how differently they can perform across different sorts of data sets. Okay? Any questions? All right, so otherwise, remember homework 3 is due today, and do try and knit your R markdown not in the last 30 seconds, because you might run into issues.